question 1 introduces Hess's law, which is the key to most of the questions, at least in the first load of questions in this section. So to put it in words, Hess's law says that delta H is independent of the pathway taken, provided initial and final states are the same. So I think it's quite important to be clear what that means. So let's think about an analogy. So if we think, instead of enthalpy for the moment, about altitude above sea level. Okay, so here's the Earth. Okay, and here's Hereford, which is at an altitude of 61 meters above sea level. And then over here somewhere is Kilimanjaro, which is at an altitude of 5,895 meters. So what that means is that if you went in a straight line, as it were, obviously around the curvature of the Earth, but if you sort of went directly to the top, like that, then the change in height would be 5,895 minus 61, which is 5,834 meters. Now suppose instead of doing that, you decided to take an alternative strategy, which would be to sort of go down to the South Pole, then go into space and do some enormous complicated route, and then land on the top of Kilimanjaro like that. Okay, so you've taken a completely different route, but you can see that the difference in altitude when you stop compared to when you start is the same. It really doesn't matter how complicated a route you've taken in between. However, if we broke this journey down into steps and said, right, let's add up the altitude changes for all these individual steps, what you can also see is that the sum of those altitude changes, if we add them all up like that, must still come to 5,834, because otherwise the final answer, the difference in altitude, wouldn't still be 5,834 meters. It wouldn't make sense. So that's really what is almost too obvious to mention in the case of altitude, but which is also true in the case of enthalpy, which is that it doesn't matter whether you go directly or whether you break it down into a whole series of steps, sometimes going by a very strange route, but if you add together delta H for each of those individual steps, they will add up to the same overall enthalpy change. And that's true provided initial and final states are the same. So that means you've got to be careful about things like state symbols, because obviously, if you end up with, for example, steam instead of liquid water, that's not the same, and so the enthalpy change won't be the same. But as long as you're careful about that, Hess's law is a tremendously powerful way of finding out what delta H is, often without having to measure it. So long as it's been measured for enough other processes, if you can combine them together, you can figure out what delta H is for any reaction, and that's an immensely powerful thing. Okay, so question 2, we're putting Hess's law into effect. So it gives us a reaction, and our job is to find delta H for that reaction. And what's going to make it possible is that we know the enthalpy changes of formation of each of the compounds involved. So you need to remember from the stuff you did in the first section on enthalpy what delta H of formation means. It's absolutely critical you remember what the definition of that is, otherwise you really have no idea what the significance of these numbers is. So remember, it means the enthalpy change when 1 mole of the compound is formed from its elements. in their standard states. So for ammonia, it means you're making 1 mole of ammonia from half a mole of N2, right, because you need half a mole of N2 to get a mole of nitrogen atoms, and 1.5 moles of H2, because again hydrogen normally occurs as H2, and you need 1.5 moles of H2 to get 3 moles of hydrogen atoms. So that's what we mean by enthalpy change of formation, and a lot of these Hess's Law questions revolve around that. So the way we're going to set it up is by drawing what people normally call the Hess's Law cycle. So that means we write the equation across the top that we're interested in. Okay, so that's the target, if you like, delta H across there. And then we're going to use these data. So, as I say, these relate to reactions where these compounds are formed from the elements. So we've got 1 nitrogen, so that's half a mole of N2. Okay, it's not just N, the element, because obviously nitrogen doesn't exist as N atoms, it exists as N2 molecules. So we need half a mole of N2 to give you a mole of nitrogen atoms. Altogether, we've got 3 plus 1 is 4 moles of hydrogen, which is 2 moles of H2. And we've got 1 chlorine, so that's half a mole of Cl2. So those are the elements we need. And obviously, because this equation is balanced, that set of elements could be used either to make these compounds or to make these, because the number of atoms of each is the same on each side of the equation, and therefore you need the same amount of each element to go either that way or that way. So delta H of formation is the enthalpy change when you take these elements and you convert them into the compounds. So that means we can write arrows going in the direction of formation, saying, right, going from the elements to form the compounds is that way. And if we're making a mole of ammonia, that's minus 46.0. And we're making a mole of HCl, that's minus 92.3. And if we add that up together, we get minus 138.3. Okay, so if we take those elements and we combine them together to make a mole of ammonia, that's the enthalpy change. Minus 46 means that much energy, remember, is given out. It's an exothermic reaction. And to make a mole of HCl is minus 92.3. So if we're going to make both of them, the total change for going up there is minus 138.3. On the other hand, if we take this set of elements and we use them to form ammonium chloride, which we can do because it's the same set of atoms just rearranged in a different way, but you can see if we go this way it's minus 315 kilojoules per mole to go up that way. So that's getting the data set down. What we can do now is to invoke Hess's Law, and Hess's Law says that this is the delta H we're interested in, but if we achieve that overall change indirectly and do it in 2 or 3 or 17 steps, and we add up delta H for each of those steps, it will come to the same number. And that's the key to the calculation. So we can make up an indirect route that starts where this starts, over here, and ends where this ends, over here. So we're going to add up these 2 steps, which take us from here to there, the same as the overall reaction. Why are we doing that? Well, because we can work out what delta H is for each of those steps and then just add them together. So what's this first one? Well, you can see it's the same as that one, except it's going in the opposite direction. Okay, so it's minus 138.3 if we go that way. And what that means is that it will be plus 138.3 going this way. If you're not completely convinced about that, let's think of it on a graph here. If we put enthalpy on this axis up here, we can mark these 2 things, these 2 states on there. So we can say, right, here's our half mole of nitrogen plus 1.5 moles of hydrogen plus half a mole of chlorine. Okay, so that's that energy level or enthalpy level. And then down here, because it's an exothermic change when we form them, so we're going to a lower enthalpy level, we've got ammonia down here. Okay, so you can see that from the data we've been given, if you take those elements and you form the compound, which is what delta H of formation is, that's minus 46 minus 92.3 is minus 138.3. And you can see from the graph that this way is just the opposite of that. So if this is this energy level and that's at that energy level, the difference between the two is the same size, but the arrow's going in the opposite direction, so the sign is the opposite. And that's all you do in all of these Hess's law calculations. If your arrow is going the opposite way from the data you're using, all you do is change the sign. So we can now get our answer, because we can get that delta H for the reaction, remember delta RH is shorthand for enthalpy change of reaction, so delta RH is equal to the enthalpy change for the first leg, which is plus 138.3, plus the enthalpy change for the second leg, minus 315, and that gives us our answer, which is minus 176.7 kilojoules per mole. Okay, so that's basically how a Hess's law works. These diagrams are really important, and once you've got used to a few of them, they're not difficult. The one thing you might consider is that we didn't really need to work out how much of each element we needed and what form the element was in, because it came out in the wash. You know, if we'd got it wrong and decided, you know, it was N13 or something instead of N2, the number of moles would have been different, but it wouldn't have affected this calculation at all, because whatever form these are in, the same number of moles, if you like, are created when you come down this way as are destroyed when you go up that way. So what I'm saying is that in some ways that's a waste of time in terms of the calculation. So what I would often do, and I think it's fine to do this, is to just simplify this by just writing elements at the bottom, because it doesn't change the calculation in any way. It just saves you time, and it saves the risk that you might make a mistake, and write the wrong formula for an element or something. The important thing though is look carefully at the data in the question and make sure those data are enthalpy changes of formation, because you can only do this and put elements at the bottom if they're enthalpy changes of formation. Some Hess's law questions, as we'll see, use different kinds of enthalpy data, and then you need a different kind of cycle. Question 3 works essentially exactly the same as question 2, but it's obviously a more complicated equation, and so that just means that we've got to be extra careful in implementing it. But we're going to set it up in exactly the same way. We begin by recognising that the data we're given are enthalpy changes of formation, because that's the key to deciding what to do next, which is to say, right, if that's the case, we can set up a cycle like we did before that has elements at the bottom. And then we can remember that these numbers we're given, enthalpy changes of formation, are the enthalpy changes when you take those elements and you use them to form the compounds. So we can put on arrows like this and like that. Okay, so we're going from the elements to form the compounds. That's the definition of enthalpy change of formation, and that's how you know which way the arrows go. Okay, going from the elements to form the compounds in each case. And we can put the numbers on. So, to make each mole of plus N2H4, it's plus 51. Notice enthalpy change of formation isn't always exothermic. Sometimes the energy you have to put in to break the bonds in the elements is greater than the energy you get back in the compound you formed, and that's the case here, which is why it's endothermic. So you've got to be careful with these signs, because they can be either positive or negative. So, it's plus 51 for each mole, but we're making 2 moles of N2H4. And that's very important, because that's got to be taken account of in our numbers. So we've got plus 51 times 2, and we're making a mole of N2O4, which is plus 9. Okay, so we've got 2 lots of 51 is 102, plus 9 is plus 111. Okay, so to make those compounds on the left hand side from the elements, is plus 111. If we go up on this side, we've got the number for water, so that's minus 286 times 4, because again, you've got 4 moles of water, so it's minus 286 for each mole, but you're making 4 moles, so it's minus 286 times 4, which is minus 1144 kilojoules per mole. What about the nitrogen? Why did I miss that out? Well, it's still the element, because of course nitrogen is the element, so there you would just be forming N2 from N2, so there's no change, and therefore there's no delta H contribution. Okay, so those are the data you've got to play with, and then again we invoke Hess's law, just like we did before, and we say, right, this is the delta H we're trying to find, and what Hess tells us is that we can do that journey in 2 legs. We can come down here and then up there, and the sum of those 2 legs will equal delta H that we want to know. Okay, so we just get delta H equals, first leg is the same as that one but going in the opposite direction, because we're going down here and the data we had were for going up there, so we change the sign. So it's minus 111 to come down here. But going up there, well, that's just the same as that. Okay, going in the right direction there, so that's minus 1144, and that comes to minus 1255 kilojoules per mole. So that's your answer. So you can see this time it's very exothermic, and that was driven by the fact that breaking down these compounds into the elements was exothermic, and then converting those elements into these was exothermic again. So both legs are exothermic, so you end up with a very big exothermic number altogether. This reaction, interestingly, was used historically for propelling rockets. And partly that's because it's very exothermic, so it generates a lot of heat energy, which makes gases expand and helps drive the rocket. But the other reason is that under the conditions that these propellants were stored in the rockets, they were liquid because it was refrigerated a little bit to turn them into liquids, whereas these, once the rocket burns and all that energy is expended, of course these will be gases because it gets very much hotter. So if you think about the way a rocket works, you go from these very compact liquids stored inside here, and once you let them react, they turn into gases which have a much bigger volume, and the only place that that gas has to go is out the rear end. And from Newton's third law, if the gas is shooting out that way, the rocket's going to shoot up that way as a reaction, and that's what drives it forward. So this was chosen as a good reaction, partly because a lot of gas is produced from these small volume liquids, and that gas has got to expand somewhere, so it shoots out the nozzle at the back, but partly because it's also very exothermic, which means that lots of heat energy is generated, which makes the gases expand more and gives you a bigger force driving the rocket upwards.